You know what's funny is that was Hope.
It was?
Yeah, that's why it was really funny.
Was she calling into the class or what?
No, she was calling Walker on Walker's phone.
Oh,
But
I see.
Sorry.
Acceleration mirrors the direction and the magnitude of the force. Okay, so wherever I have the greatest force, I'm also going to have the same direction and magnitude of acceleration. So the magnitude of the force slows down the mass moving away from the equilibrium. It speeds up the mass moving toward the equilibrium, and acceleration is 0. We've already answered the question, how does mass get past the equilibrium point? So if I add in the acceleration here, this is just F equals ma, right? Acceleration equals F over m. 20 newtons divided by 5 kilograms gives me 4 meters per second squared here, and then 2 meters per second squared here, then 0 meters per second squared here, then -2 and -4, and then it goes back again. Okay, so we've got position to think about, we've got the force that's going to restore the mass or the oscillation, and we've got the acceleration of the mass. And again, keep in your mind that the acceleration and the force mirror each other, but then the velocity is going to be the opposite of that. So the velocity is going to be the maximum at the equilibrium position, 0 at the maximum displacement, and slowing down if going towards the maximum displacement, speeding up if it's going towards the equilibrium position. So if you keep in mind that the velocity, its features are opposing the force and the acceleration, that would be one way to kind of keep all of this stuff straight. Okay. I don't really need to remind you, I don't think, about the vectors that are involved.
So Marshall,
Yeah.
so when we deal with oscillations in calculus,
Uh-huh.
are you aware of that?
Yeah.
Like,
Well, I'm
No,
asking
I'm
because
not aware that we can deal with oscillations.
no, I'm not saying deal with like the actual what it is and what it looks like. What is that signifying? Because I don't think it's signifying this. So this isn't like imperative physics, but like what's the difference?
I guess I'm not sure what you're talking about.
Because well, when you deal with oscillations,
So no, I don't know what you're dealing with.
when you deal with oscillations in calculus, it's like on a graph, and it just like the point of oscillation is that you can't see where it's going because it's so small and it's going up and down so much. So I was wondering, like, what does that signify, and what does this obviously
Well,
signifies?
we'll graph this too.
Will it do this?
Yeah, it'll
same
be a
thing?
sine wave. It'll be this.
Okay, I'm
Okay, and
wondering
we'll
what-
create a formula to figure that out.
Okay, I was just wondering what the difference
Yeah.
is.
So notice then that at its maximum extent here, its velocity's 0. That's the vector, but its force and acceleration are at their maximum. Here, all three of them are kind of at their midpoint, and then here we have 0 acceleration, 0 force, and maximum velocity. And then as they go the other way, they diverge rather than are the same as each other. And so that's just kind of an illustration of that we don't need to sit on too long. But we need to get out of the illustrations. Okay, that should be good. Okay, so that's the model of an oscillation, and we'll use that to create a mathematical model of what we're talking about. Let me go a couple more minutes and then we'll take a break. What about springs that are located vertically? The addition of a mass to a vertical spring adds the force due to gravity, causing the spring to be longer at equilibrium than it normally would. So what I mean by that is if my spring is just hanging here, that would be its equilibrium point, and if I compressed it, it would compress a certain distance, and then that would create a restoring force back toward the equilibrium. But it's obviously not going to go much farther than that because there's no mass on it causing any kind of a back and forth oscillation. So if I hang a mass on this, my equilibrium point is actually going to be right here. Okay? My equilibrium point is going to be where the mass ends up hanging. Even though I'm stretching it past its original equilibrium point, what we're going to say is that this is our new equilibrium point. And what we'll find out is that if I now exert a force on this down to about here, the excursion or the cycle will be the same width on both sides. So if I let it hang naturally with the mass there and I pull down, then however far I pull down will be how far it goes back up. And that will be my oscillation.
Is that always true? Really?
Yes.
Oh.
Yes. There's no difference. Once you let it sit there and then you start it, there's no difference then between that and a spring on a horizontal plane. But if we were to say that was our equilibrium point, then we're going to have problems, right? Because then it would just go like that. And it would bounce up a little bit and come back.
So when we're trying to find force for a vertical one, do we just add the normal force that happens because it's a spring and then the force due to gravity?
Yeah, it'll still, the excursion here, the restoring force will still follow the same formula. The F equals negative kx.
But don't you have to add in gravity?
No. Not as far as, well, yeah, as far as the force goes, you do,
Yeah.
but the force will, well, let's do this. Let's walk our way through it. So all we're going to do is shift the equilibrium to a new position, okay? We're just going to say that instead of this point being my equilibrium point, like it would be on a horizontal surface, okay, so if I put a mass there and it's at its normal length, that would be like this setting. But if I let this hang down now, all I'm doing is shifting my equilibrium force. And that will be at the point at which the restoring force from this point to this point will be in equilibrium. So this is going to be mg, right? Right?
Yeah, sorry.
Okay, and this is going to be my restoring force. And so this is going to be negative kx. And so what we're going to do then is say at this point then, so you're absolutely right. In this sense, we do add in gravity.
Yeah.
Okay, but at that point, you would agree that gravity is balancing the restoring force of the spring, right?
Mm-hmm.
Yeah? So it's going to be force, the net force is going to equal 0 because it's not moving, right? It's not accelerating at that point. And at that point, the weight is going to equal the restoring force. And this is the restoring force for this equilibrium point. Okay? This is the restoring force for this equilibrium. Okay, we've got a new equilibrium down here, but the x that we're talking about for this point is going to be the distance that the mass pulled it down. Okay, so mg is going to be positive, and this is going to be the restoring force holding mg in equilibrium. That's going to be negative. x0 is the new equilibrium point from which everything else is measured.
Do we ever need to know the original Like, does that actually matter for
You
calculus?
could be asked to figure out what the original point was. Okay? So you won't need it to know it in terms of it'll help you find something else, but you may be asked to find what the original point was. Okay? So x0 is going to be the new equilibrium point from which everything else is measured, and that will be a certain distance from the original equilibrium point. Okay? So, the difference in the original x equals 0 and the new x0 is given by, since I've got a balance here, right? These two forces are balanced. I can say that mg equals kx0, and I can find out what that original point was by dividing mg by k. So whatever that original point was, where it's just sitting there, and now it's hanging by a mass, this distance, this x0, is going to be given by mg divided by k. Okay? So if I do need to find it, that's how I would find it. Okay? And it's just a matter of remembering that at this point, these two forces have to be balanced. And if you set them equal to each other, you can solve for that x. Okay? Even though we have a new equilibrium point, the same k can still be used. Okay? The spring constant doesn't change just because it's stretched, right? It's going to be the same no matter what. So I can still use that k. And so we have a problem here. When a family of 4 with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compress 3 centimeters. Okay? What is the spring constant of the car's springs, assuming they act as a single spring, and how far will the car lower if 300 kilograms is added rather than 200 kilograms? So before the weight of the car is ever added on to the springs are at their natural point, right? So I've got my springs here, and they're sticking up from the wheels. And we could say that this is the original 0 point. At this moment, they're compressed by 0 amount, and the restoring force is going to be 0 newtons. Okay? So I have no weight on them. I do know that g is 9.8 meters per second. I know that mass is 0. And I don't know what the spring constant is at this point, but I know that x is 0 and negative kx is also 0 newtons. Okay? When the mass of the car is added, the springs are compressed. In this case, we aren't told by how much, but we don't really care because we're going to treat this as if it's the new equilibrium. Okay? That's our new normal, our new equilibrium. Okay? Doesn't matter, and that gets back to your question, DJ, do I need to know that original point? For a problem like this, no, I don't really care, because this now is my new normal point. Okay? So we're going to treat this as if it was the actual equilibrium point, even though the springs are now partially compressed. Okay? And now that I know that the mass is 1,200 kilograms, the car, I know that the weight is 11,760 newtons. Therefore, because it's balanced with the restoring force of the spring, I know that that's negative 11,760 newtons. Okay? But I don't really care what that is.
Wait, why is it equal?
Because it's not in motion. It's not accelerating, right? If the Once it comes to rest on the springs, it's not accelerating.